Okay, so we moved on from relative dating and talked about absolute ages and how we go about assigning them to rocks or earth materials. And that's really through the process of radiometric dating, and it relies entirely on radioactive decay and the predictable nature of it. But through relative dating or just working out the relative order of events, early geologists assembled the entire geological time scale, which is shown in the slide below, and it was really entirely based on the presence and absence of particular fossils. Okay, and so you can go around and correlate rocks to one another on the basis of fossils. And if you do that, you find that there are some pretty obvious things that jump out. There are lots of these big drops in global diversity. This is showing the global diversity in the fossil record at the genus level. And you can see that there are these extinction events where large percentages of the organisms that were present before, they don't appear after. And so those make really good divisions for the time scale because they're pretty identifiable around the world. And so you can see that a lot of these, in fact, this is the end of the Paleozoic here at the Permian-Triassic boundary. This is the end of the Mesozoic here, 65 million years ago at the Cretaceous-Tertiary boundary there, right? And you can see that those are the Paleozoic Mesozoic boundary there, and then the Mesozoic Cenozoic boundary. Those are two of the most fundamental divisions in the geological timescale, and they're based on these large extinction events. Right. Now, early geologists worked all of that out, not knowing how old any of these rocks were. Right. And it turns out that the whole Phanerozoic, or the base of the Cambrian here, is about 540 million years ago, whereas the Earth is about 4.5 billion years old. And so this only represents 540, 550 million years. The Earth is 9 times older than that. Okay, but the most basic division in the geological timescale is here between what we call the Precambrian, and that's just all of these old rocks that don't have fossils in them, and then the Phanerozoic, everything after that. Right? It wasn't until people developed techniques to find the absolute ages of rocks, really radiometric dating, until we understood exactly how much time those rocks actually represented. Now, radiometric dating just relies on the fact that some isotopes will decay into other elements over characteristic timescales. And so there are some examples here of radioactive isotopes, potassium-40 or uranium-235, carbon-14, right? Most people have heard of carbon dating. That relies on this carbon-14 isotope. And carbon-14 specifically will decay into nitrogen-14 over a characteristic timescale. Carbon, not all carbon decays, right? Carbon-12 and carbon-13 are stable isotopes, and we'll talk a little bit about how we use those in the earth sciences in a couple of weeks. I think the week after spring break we'll talk about that. But the carbon, not all carbon is radioactive. Carbon-14 decays into nitrogen-14, and it has a characteristic half-life, which is what this chart over here at the left in the homework is talking about. And the carbon-14 nitrogen-14 half-life is about 5,730 years. Okay. Now, a half-life is just the way that radioactive isotopes decay. They decay in a very predictable fashion, but it's not a linear decay, right? If it was linear, it would start at 100 and go to 0. This kind of an exponential decay starts at 100, and then as one half-life passes, 50% of the original parent atom has decayed into the daughter atom. But as a second half-life goes by, you've only lost half of what was remaining. So you're down to 25%, and then another half-life goes by, you're down to 12.5%, and so on, right? But each one of these half-lives is the same amount of time, right? And so for carbon-14 and nitrogen, that's 5,730 years. So after one half-life, that's 5,730 years, and you have half of what you started with left. Then after another 5,730 years, so whatever that is, 11,460 years, you've got 2 half-lives, right? 75% has decayed into nitrogen, and you have 25% of the carbon-14 you started with left. Okay, that's how half-lives work, right? You start with 100, you lose half after one half-life. After the second half-life, you just lose half of what was left, right? So you have 25, and then half of what was left. So you have 12 and a half, and that's a typo. It looks like 80, that should be 87.5, right? Yeah, it's not in a text box. I wonder where that figure came from. Yes, okay. And so, and that progresses, right? And so you never actually get back to zero, or down to zero rather, of the parent atom here, the parent isotope. There would be a trace amount left almost forever, but you certainly lose the usefulness after a certain amount of time, right? After 5 half-lives, you're down to only 3% of the parent atom, and that would get even lower and lower. And so, for carbon and nitrogen, we're talking about 5,000, less than 6,000 years for one half-life. And so within, 50,000 years or so, this technique is no longer really viable because there's so little of the carbon-14 that it started with left. Okay. And so here are some common decay pairs and their half-lives. They vary widely, right? Rubidium strontium has a half-life of 48 billion years. The universe is only 13.5 billion years old. You might wonder how we can calculate that, but it's because of this fact here, that all radioactive decay follows this very predictable logarithmic decay, where you have one half-life, 50% is left, then 25% after a second half-life. And so you can follow that all the way up here and make very precise measurements on rubidium strontium and find that the half-life should be out here at 48 billion, 48.8 billion years. Anyway, so that's how these really work, how these half-lives. And so half-lives work. And so in the questions here, we're asking about a solidified lava flow that has these zircon minerals in it. These are just a mineral, zircon, that can substitute in a lot of uranium. And so it's also quite resistant to erosion. And so it's a very, very good mineral for dating, for using radiometric dating techniques. And so this says that there is 71% of the parent atom, uranium-235, left, and 29% of the daughter atom, lead-207. Okay, and so uranium-235 and lead-207, if we go back up here, 235, lead-207, it has a half-life of 713 million years. Okay, and so if we start with 100% uranium and no lead, after 713 million years, we're going to have 50% uranium and 50% lead. Okay, you're essentially right here, right? Okay, now that's not what we have. In fact, we have 71% uranium and 29% lead. And so if we go up here and look at this table, percentage of parent atoms, percentage of daughter atoms. Okay, well here, 70.7 and 29.3, 71, 29, that's pretty darn close. Okay, and so that says that's 1/2 of a half-life. Okay, and so this age equals 0.5 times a half-life. That's equivalent to saying it's one half-life. One half-life has passed, and yeah, you can see that here actually. 1/2 of a half-life is up here at 70.7 and 29.3, right? And so the half-life for uranium-235 and lead-207 is 713 million years, like we said. And so you just multiply that by 0.5, since one half-life has elapsed, and you would end up with, 713 divided by 2, 353, 56.5, right? Something like that, if I did my math right. And so the answers, we've answered this question now here. We can't get all the way to the bottom of that window. Let me move it up like this. Okay, so how many half-lives have passed? Well, we decided that it's been about 1/2 of a half-life. the absolute age based on that we calculated. How old are the rock layers below the lava flow? Well, we don't know anything about them, so we know that they're below, right? And so we can say something about it, but we don't know anything about their absolute age, right? And similarly, question D there. Hopefully the rest of these are doable with that. But if you guys have any questions, please feel free to email me, and I'll do my best to answer them. Thanks.